When you think of rocket science, you probably think of something similar to this. Large scale, a huge team, and millions in funding. But rocket science still applies on the smallest of scales, in water rockets. In this video, we'll take you through the process of making a water rocket and show you how we worked through each problem. The design objective is to build a rocket that is stable, safe enough to be launched, and remains intact during the course of the flight. The rocket must include a parachute for a safe landing and an egg that should not get damaged during the flight. Additionally, the rocket must land within a 50 by 50 square centered on the launch point. The team whose rocket travels the furthest distance in addition to meeting all the conditions of the design objective is placed as the winner.
In order to do all of these, individual components of the rocket must be optimized. A spreadsheet, a list of equations, and a simulation were our tools for building a successful water rocket. The spreadsheet we made helped us to understand the physics of our rocket and was useful for displaying propulsion.
The thrust in the water rocket is produced by the compressed air expelling water through a nozzle at the bottom of the rocket. Newton's third law stating that every law has an equal and opposite reaction means the rocket will blast off. An important part of this stage was determining a water fraction, and this determines the impulse the rocket receives. If the water fraction is too large, the rocket will have a higher overall mass, preventing it from achieving sufficient acceleration at launch. On the other hand, if the fraction of the water is too little, the water rocket will be too light and unable to gain sufficient acceleration. Impulse is the change in momentum or the product of force and time. Thus, to optimize impulse, we need a large force times a large time, meaning a large thrust is required. Through our calculations, theoretically, the most favourable water fraction is around 0.4. Experimental data will be collected to confirm this.
Another problem to face was stability, including the number of fins to have, where to place them, and their shape. The best case would be to achieve directional stability, which is where the rocket goes straight up, not deviating from an estimated path. 3 fins are better due to less drag on the rocket, and theoretically, elliptical fins are the best shape. Finally, we had to concentrate on how large the parachute was going to be. Too small and the parachute won't create enough drag so the rocket will reach a high terminal velocity, risking the safety of the egg and causing the time of flight to decrease. Too large and the parachute will be too heavy, meaning the rocket won't go as high and will be more unstable due to a heavy nose. The solution lies in an area in the middle, where the parachute has enough drag without being too heavy. All of these factors can be inputted into Excel and modeled in Unity to make the perfect water rocket that travels the furthest distance while remaining intact and not becoming a safety hazard.
To conclude, water rockets are really good experiments to conduct, not only because they look cool when they shoot off into the air, but they're also a nice introduction to tools and processes engineers use every day, from arranging group meetings, simulating physics, and creating spreadsheets that give you quick answers to any change you want to inquire about. They're a great way for engineers to learn more about operations of rockets and spacecraft systems in a more hands-on way. Thanks for watching. We beat Group 22.